All right, this is part 2 of properties of radicals. So for example 3, it's saying using properties of cube roots. So we looked at square roots in the last example. Now we're looking at perfect cube roots, meaning powers of 3. So you can see I've got you a list over here. These numbers are all perfect cubes, and you can see if you take the cube root of each, what that produces. All right, and the cubes, like a number cubed, 4 cubed is 64, and then the cube root of 64 is 4. So a perfect cube undoes a cube root, kind of like opposite operations, like how addition will undo subtraction, that sort of thing. All right, and also with cube roots, unlike square roots, cube roots have perfect cubes of negative numbers as well, because remember a cube is 3. So if you have a number 3 times, like a negative 3 times, negative 2 times negative 2 times negative 2, that's going to give you negative 8. So the cube root of negative 8 is negative 2. So on the left side, here's all your positive cube roots, and on the right side is your negative cube root. So they're the same, it's just with the negative number of that. All right, let's get started. A part says A part says the cube root of negative 28. All right, so the cube root of negative 28. So I need a perfect cube. This is not a perfect cube, but if I look down through here, I can see that 64 times 2 is 128. All right, so all I'm doing is scanning these numbers. These are all perfect cubes, and 128 is not in this list. 125 is. But I can determine that 64 goes into negative 128 twice. So I can rewrite this as the cube root of negative 64, and I do want to use the negative one over here, times the cube root of 2. Now what I did is use the property, the product property, meaning if I multiply negative 64 times 2, it gives me negative 128. So I'm just rewriting this so that I can simplify it. Now I know from this chart here, if you don't know on your own, hopefully you know from the chart, the cube root of negative 64 is negative 4. So negative 4 times the cube root of 2. There's no perfect cube in 2, so you just leave it as the cube root of 2. So this is as simple as it will go. All right, B part says the cube root of 125 times x to the 7th. If you look down through here, 125 is a perfect cube. 5 cubed equals 125. So I'm going to say cube root of 125. And then 3 goes into 7 twice. So I'm going to say times the cube root of x to the 6th and times cube root of just x to the 1st. All right, so cube root of 125, you can determine from the chart here, cube root of 125 is 5. So this one is simplified to 5. The cube root of x to the 6th, what you do is just take the index and it has to divide evenly into the power. That's why I changed it to a 6 times 1. Same base, you add exponents, right? Same base, 6 plus 1 is 7. But I changed it to 6 times x to the 1st so that this one can be reduced and pulled outside the radical sign. So 3 goes into 6 2 times, so that becomes x squared. And then, of course, the last one just becomes cube root of x. It stays, it doesn't become anything, it just stays what it is. All right, and that is this B part simplified. So 5x squared cube root of x is equivalent to cube root of 125x to the 7th. All right, now we need to do cube root of y divided by 216. All right, so this is to the first power if it doesn't have a power. 216, if we look down through here, 216 is the same as 6 cubed. So we're going to rewrite this as cube root of y over cube root of 216. Cube root of y cannot be reduced, so we leave it. Cube root of 216 is actually 6. So these aren't too difficult if you know your perfect cubes, or if you have a table with perfect cubes on it. All right, cube root of 8. Okay, if we look here, 8 is in this list. I would need to write this as 3 times 1 though, because properties of exponents, I can rewrite my exponents. And then 27, again, that's in my list of cubes. 3 cubed is 27, and then x cubed. So right off the bat, I can rewrite this as the cube root of 8 times the cube root of x cubed times the cube root of x. And on the bottom, I can write the cube root of 27 times the cube root of y cubed. All right, now everything that has an index of 3 and is a perfect cube will be simplified outside the radical sign. So cube root of 8, you can see cube root of 8 is 2. This is the cube root of x cubed, so the index 3 and the power of 3 cancel and leave just x. And then this is just cube root of x to the first. That stays under the radical because you don't have 3 of them to pull out. All right, cube root of 27. Cube root of 27 is 3. And cube root of y cubed is just y. If this still seems a little difficult for you, instead of writing cube root of 8 and going straight to 2, you may want to write cube root of 2 cubed so that you can see the index and the power cancel and you know that the 2 is what comes out. Same thing here, 3. So index of 3 means you've got the cube root of 3 cubed. 27 is 3 cubed. Whichever way makes it easier for you, please do so. All right, this is a self-assessment. So you can see that these are square roots now instead of cube roots. So it goes back to the previous example. I want you to pause the video, take a few minutes, and see if you can simplify these on your own. Then down here's a vocabulary, a math reasoning, a couple math reasoning problems. See if you can answer these, and then we will check them together. All right, hopefully you got finished. Let's see how you did. All right, 24 can be rewritten as 4 times 6. It can be rewritten as 2 and 12 and other things as well, but we chose 4 and 6 because 4 is a perfect square. And since we're dealing with square roots, we need a perfect square in order to break it down. 6 is still 2 times 3, neither is a perfect square, so we have to leave it inside. So you can see the square root of 4 becomes 2, the square root of 6 just comes along. All right, the next one says negative square root of 17 over 100. So I can rewrite that as negative times the square root of 17 over the square root of 100. 17 is a prime number, so we're going to leave it right like it is under the radical sign. The square root of 100 is 10. 10 times 10 is 100. 75 is not a perfect square, but hopefully quickly you could see that 25 times 3 is 75. And 25 is a perfect square. 5 times 5 is 25. N to the 5th is not a perfect square, but n to the 4th is. Properties of exponents, I can rewrite this as n to the 4th times n to the 1st. Remember, when you're multiplying same base, you add exponents. 4 plus 1 is 5. So this is still equivalent to that. So what we're doing is simplifying. We're just rewriting it. So the square root of 25 is 5. The square root of n to the 4th is n squared. And then the square root of 3 and n stay under your radical sign. The last one here, square root of 36, is a perfect square. Z squared is a perfect square. So that simply reduces to 6 over z. All right, vocabulary is the square root of 63 in simplest form. Explain. No, it's not, because you can rewrite 63 as 9 times 7. 9 is a perfect square, so you can rewrite that as 3 square roots of 7. The next one says simplify the square root of 8 squared. Find the value of the original expression and the value of the expression in simplest form when x is negative 1. All right, so if I simplify this, 4 times 2 is 8. The square root of 4 is 2. We're going to leave x. Well, actually, square root of x squared is just x. And then the square root of 2 is not a perfect square, so it stays underneath. When we let x equal -1, it ends up being -2 square roots of 2. So what do you notice? That these have different values when x is -1. All right, the last one are the expressions 1 over 3 times the square root of 2x and the square root of 2x over the square root of 9 equivalent. Explain your reasoning. I put yes. So if we leave this here, we can say the square root of 2x over the square root of 9. The square root of 9 becomes 3. You can assume that 1 in front of your radical sign, so that becomes 1/3 times the square root of 2x, which means those are equivalent. All right, I hope you did well with those, and now we're going to move on to example 4. All right, rationalizing the denominator. Rationalizing the denominator works because you multiply the numerator and denominator by the same non-zero number a, which is the same as multiplying by a over a. When you multiply anything by something over itself, that's equivalent to multiplying by 1. So to rationalize your denominator means we need a rational number here, which means we cannot have a square root in the denominator. So for a part, I can multiply the top and the bottom by square root of 3n. Okay, so square root of 3n over the square root of 3n is equal to 1. If you multiply anything by 1, you're not changing it. Okay, so this is just an equivalent form. So now we're going to have square root of 5 times square root of 3, which is square root of 15. We still have our n there as well. And then on the bottom, we have a square root squared. So this would be 3 times 3 is 9, and this would be n squared. So the square root of 9 is 3. The square root of n squared is just n. So when you multiply something by itself, you're rationalizing the denominator because now this is a rational number. All right, the next one says 2 over the cube root of 9. So remember, when we have a cube root, you've got to have a multiple of 3. So 9 is 3 times 3, so we need the cube root of 3. We need one more 3 there. So we're going to multiply the top and bottom by the cube root of 3. Now, that's equivalent to 1, so we didn't change it. So now on top, we're going to have 2 times the cube root of 3. And on the bottom, we're going to have the cube root of 27, or 3 cubed. So it's going to be 2 times the cube root of 3 over 3. And you can have you can have a irrational number on top, meaning you can have a radical sign in the numerator, just not in the denominator. That's why it's called rationalizing the denominator. So we need a rational number in the denominator. All right, the last one here says 5 over cube root of 32. This is a self-assessment, so I want you to pause the video, take just a minute, and see if you can rationalize the denominator. Remember, write numbers that are perfect cubes, and the cube root will cancel a perfect cube. Sometimes you have to be a little creative with these. So see if you can get creative and rationalize the denominator for the self-assessment. All right, let's see how we did. I didn't do this one yet because I feel like it's important that you understand how to do this, so I'm going to walk you through it. All right, so we have 5 over the cube root of 32. So we have the cube root of 4, the cube root of 4, and the cube root of 2. Now, how do I know that? Well, you have to play with numbers a little bit. So what is 32 if you rewrite it? It's 4 times 8, and 8 is 4 times 2. So what I did was just write this as what it would look like if you broke that down. Now, I need a perfect cube. I've got 4 and 4, which is a perfect square, but I need this one to be a 4 as well. So if I multiply the whole thing by 2, so I'm going to multiply by the cube root of 2 on top and bottom. That's going to give me 5 cube roots of 2 over 4. Because this becomes 64, and the cube root of 64 is 4. Hopefully you got that.